Hi everyone, welcome to this lecture on structure learning. So this will also be an online lecture, and the reason for this is because on the day when I'm supposed to have this lecture, which I think is the 18th. I think it's the 18th. I won't be around. I'll be in Kenya. Uh, yeah, so I won't be able to give you this lecture in person. So what I'm going to do here is I'm going to go through this entire lesson and I'm going to upload it onto Moodle early. And if you want to watch it earlier, you're welcome to do it, but it was meant to go on of that week of the 18th. Okay, so let's get started. So what is structure learning? Well, let's find out. So structure learning is a concept in graphical models. And notice here, the topic now changed from representation to inference, and now it's learning. So now we're on the learning side of things. The lecture before this one would have been the lecture on parameter estimation. And that lecture will be, I think, on the if this one is on the 18th, then that lecture would be on the 11th of September. Yeah, so you would have that lecture would have been in person, and this is now the second lecture on learning. Okay, so yeah, so I told you before about the structure of the course. There's the representation side of it. Okay, there's the inference side of it, and then there's the learning side of it. And after that, we get the causality, and then after that we get the decision problems. Okay, all right, so I'm gonna continue. Okay, so like all of my lectures, I always start with the problem statement. So let's see, before we actually formulate the problem, which is this part here, let's first talk about some assumptions that we need to make. Okay, so when talking about assumptions in graphical models, there's a worldview, and that's the Bayesian worldview. Okay, you get the frequentist worldview and the Bayesian worldview, and I covered these different worldviews in the first lecture when I spoke about the Bayesian paradigm, which is to have a posterior distribution modeled with priors and averaged over all possible hypotheses. Okay, so the Bayesian philosophy is really around that idea of averaging over all possible hypotheses. So you picked the hypothesis as a prior, and you multiply it by the likelihood and divide by all possible other hypotheses that could exist. Of course, this is difficult because you would need to then actually know what the other hypotheses are. But in this worldview, there's something called a true distribution. So this is the distribution that we often can't see in real applications. This true distribution is what's really going on. And in machine learning, we often want to be able to model this distribution. So let's suppose that the true distribution, and it's obviously latent, it's hidden away, and we denote this, the true distribution is as P star. In graphical models, there's something called faithfulness as a property of the models that you learn. And that says that the G star, which is the graph structure that you're going to learn, this accurately represents P star. So let's say that this is the graphical model that we learned. This G star is called the ground truth network. Okay? This is the ground truth network. So this is the true distribution, and this one is the ground truth network. So in other words, this true distribution manifests in G star. It manifests in G star. So notice that there's a star here to indicate that it's the true graph structure that represents this distribution. There could be many different kinds of G stars representing the distribution, P star, but this is one of them. Or maybe you can say that this is the set of distributions G star that represent our true distribution P star. Okay? So from this G star, what often happens in machine learning is that we actually have the data which is generated in real life. So for example, there's some unknown distribution to true distribution. The ground truth distribution is then it's modeled using a graphical model. The ground truth, yeah, it's modeled as a graphical model as a structure. So this is a structure. It's a PGM, and then from this PGM, information is sampled. Okay, this information here is called D. and this D is the one that I'm talking about here at the top. So this is often what you see in machine learning problems. This is what you get to observe. So for example, if you're collecting data on all of the students, then you collecting D. You're collecting from this ground truth structure. Okay, what actually generated the student data comes from some true distribution. Okay, that you don't get to observe, but you get to observe what manifests from that true distribution in the form of instances. So maybe here you get to, maybe there's some student data. So this is male, okay, a grade that the student has gotten 80%, and it's in maths and whatever else. All of that information that you get to observe is your D. Okay, so we call this D, and this is instance 1, there's instance 2, instance 3, all the way to instance M, and that's the data that's generated. An important observation here, and the assumption that we make, is that the data is generated independently and it's identically distributed from the ground truth network. So they are independent, which means that we don't use some of the samples to generate more samples. Okay, they're independently generated. So we generate first sample, and then we independently from the ground truth generate the second sample, independently from the ground truth generate the third sample, and so on. So that's the identically distributed part. And the identically distributed part means that all of the data comes from the same distribution. Okay, and that distribution is P star, which is manifesting in this G star. So that's important. So that's what identically and independently distributed means. This P star here, when you see the star, we're talking about the true network. This is the distribution over a set of edges, a set of, sorry, not edges, a set of variables. So that's your x, fancy x. Fancy x is equal to x1, x2, x3, all the way to xn. Okay, so that's one of the assumptions that we need to make. So at this phase in the machine learning problem, what researchers normally do is they take this data, and in some machine learning problems, they'll use a neural network to analyze this data. They'll use a support vector machine to analyze this data, to maybe understand what's going on. They use Gaussian mixture models or whatever. And I'm sure you must be thinking, why don't we just use a graphical model? Why do we need to use all of these things? Well, that's exactly the motivation that I'm trying to get across here, that you don't need to use, obviously different models give you different kinds of advantages and disadvantages, but the most natural way to represent this data is as a graphical model. In the same way, the assumption that we're making that gave rise to the data, and where the data manifests between variables through independence assumptions, which gave rise to the data in this D, you can just then model D as another graphical model. Model D is another graphical model. Maybe you might not be able to capture the identical structure. Maybe the graphical model will look differently, but the point is that you can go back and model this as a learned network. Once you model this as a learned network, you then can actually use it for prediction. Okay. What's really great is if we do have access to the ground truth structure G star, is we can use something called KL divergence to look at the learned network, and this is entropy or KL divergence. Okay, to compare the learned network, which is this one here, learned network, with the ground truth network, which is this one here. Okay, so I hope all of this makes sense. So these are the assumptions that we're making on this slide. So I'm just gonna delete all of this so we can see what I've written here. Okay, so as I said before, we assume that the data is D, and it's of this form. It's identically and independently distributed from our true distribution P star of x, right? And as I've said before, P star of x is induced by a Bayesian network, G star, okay, over all of the variables of x. So all the variables of x that were in the true distribution are now represented inside of the graph structure of the graphical model. So the big question that we often ask in graphical models is, to what extent do these independency assumptions manifest in D? And there is a beautiful property of graphical models called consistency that shows that the true distribution manifests. So in other words, everything that we need to represent the true distribution we can represent it as a graph structure G star. And then that has to do with something called faithfulness, and that's now getting into the advanced topics of graphical models. And I can leave you to research those on your own if you're interested. So I'm very excited about this lecture because this is my expertise. This is what my PhD thesis was on, and it's very much into my well, all of graphical models is something I'm interested in, but this is something that this is where perhaps maybe the best way to say it is this is where I started off by learning about structure learning for my PhD dissertation. Okay, so let's actually so let's actually talk about the problem, because this is the problem statement, right? So what is the problem? The problem is to find the best Bayesian network structure G, the best structure, okay, that represents all of the independence assumptions in P star, okay? And these we want to represent that, and all of these manifest in D. So the more pragmatic kind of, well, obviously the best case scenario, the big problem that we're trying to solve here is how do we find a graph structure G that represents P star? But the more pragmatic question here is how do we find a Bayesian network structure G that best represents the dependencies that manifest in D? So in other words, the more pragmatic question looks at actually recovering these from the data that we get to observe, not from the hidden distribution that we don't ever get to see. So in other words, the best thing we can hope for is an empirical distribution, which we can maybe try to use to get G out of. Obviously not G star, right? I hope that doesn't confuse you. We're just looking for the normal G, a graph structure that best represents the dependencies that manifest in D. Obviously, there might be others. There might be a whole class of models that best do it, but we're trying to find that set. I mean, most ideal thing would be is to find G star. Okay, I'm sure you realize that, but you'll see at the end of this talk that it's not always possible. In fact, it's almost never possible. Okay, so why would we want to do this? Well, the importance of learning a structure, a graphical model, the structure of the graphical model in particular, because the previous lecture, you know now how to, if I give you a structure, can you learn the parameters? You know that. But in this lecture, we look at the importance of actually reconstructing the structure of the network. And there's two reasons why we'd want to do this. So the first reason is for knowledge discovery. So knowledge discovery has to do with learning associations between variables that perhaps we didn't know about. So maybe if you're trying to learn associations, let's say A is influencing B, and then there's C involved here. Maybe this is our current understanding of reality, that these variables have these type of independencies. But maybe after doing structure learning, you learn that A also influences C, which influences B. So structure learning can give you insights on how variables actually interact with each other. And obviously, I don't have to convince you that this is a really great thing to know, because you probably already can think of many applications where these kinds of learning about these kinds of associations will be useful. The other reason why we'd want to learn a graphical model, the structure, is for density estimation. So if we learn a really good model and we learn the parameters of the model, then perhaps we can actually use it for density estimation, which is to make predictions. So if I don't have a structure, like in most cases for your assignment, maybe you wouldn't have a structure all the time, then you can actually just then use any structure, or you can actually learn the structure. And if you learn the structure, obviously, if you learn the structure with relative to D, you'll get better accuracy. And so we can have better probabilistic queries like P of Y given E, and so on like previously. We'll have more accurate density estimation if we learn the structure, rather than guessing it or just using our understanding of the associations. But having said that, there is a way of using your own knowledge, and this is one of the wonders of graphical models, is to be able to incorporate your expertise into the model itself. And we do that using something called structure priors or parameter priors, and there's a whole section of this talk where we're going to be looking at those. So what do we mean by knowledge discovery? So if we want to learn for knowledge discovery, which is learning the associations, okay, between variables, then we need to deconstruct G star, okay, because that'll tell us how the actual variables manifest. So so G star will say X influences Y, and so then we can take this as true that X influences Y, okay? So we need to actually we need to actually get exactly G star, not just any G. It needs to be the one where the variables have the associations. So this is particularly useful, and that's what we will need to do if it's for knowledge discovery. But something that we need to remember is that G star from one of the first lectures we had, we said that there are many perfect maps for G star. And it's a high equivalence class. In other words, there are many other graph structures that are identical to G star, not perhaps in terms of their structure, but perhaps in terms of their density. In other words, they provide the same posterior distribution. They're modeling the same posterior distribution. So then what we can rather hope to get is a set of I equivalence classes. So in other words, G star, the true structure among other structures, which are all going to give us the same kind of likelihood to the data, that make the data as likely as possible. And this year, perhaps we can use it for knowledge discovery. So we might not be able to find a single one, but we can find a class of models. This class is called the I equivalence class. Now, and an example of this is X to Y and Y to X. So in other words, these two are identical. They both encode the same density. Although the structure assumptions look different, they are actually I equivalent. And I can give you more examples, and I did give you more examples of I equivalence in one of the previous lectures with 3 variables, if you remember. Only the V structure wasn't encoding the same distribution. If you can't remember that, then I'll just remind you. So if I say X is independent of Y given Z, how can I draw the different networks that correspond to this? I can have X going to Z going to Y. So this is true. This satisfies this equation. So this here, let's say this is P star satisfies this equation. And then if you get another one, here's another one, Z, and then maybe you can go this way, okay? And then here's Z, and maybe you can go this way, okay? Obviously, the only one that doesn't, oops, okay, sorry, the other way around. That's a collider. So this one here, X and Y. So all of these networks are I equivalent. So network 1, G1, G2, and G3 all belong to the same I equivalence class, okay? The one that doesn't belong, that encodes a different independence assumption to this here, is this one, where X collides with Y, also called the V structure, which you've seen, because this doesn't satisfy this equation. Okay, all right. So let's actually look at what does this mean. I'm just going to erase this now so we can look at what does this actually mean. All right. What does this all mean in terms of identifying G star? Well, it turns out that identifying the single structure, perhaps that is associated with the ground truth distribution, is not identifiable from D. As I've just shown you in the examples that I put you on the screen, there is no way of identifying there is no way of identifying G star from the 3 structures that I showed you. The one where there were those 3 variables that I drew at the bottom here. Okay, because they all encoded the same independence assumption, and that would also mean that they're identical in D. So that's a big problem. And not to mention that data sample from the true distribution is noisy. Okay, so even with infinite data, you still might not be able to find G star. Yeah, all right. So let's also talk about what kind of heuristics we need when we're learning G star. So if we learn too many edges, okay, if you learn too many edges in G star, then you're learning deceptive edges. You're learning unnecessary edges. And also seeing that the graph structure needs to be acyclic, sometimes learning unnecessary edges actually blocks some more optimal independence assumptions that did manifest in P star. However, on the other hand, if you learn too few edges, okay, then it is not then possible to capture the true distribution. So you've got to find, when learning G-star, you've got to find a balance of edges. It can't be too many and it can't be too few. So for the too few example, for example, suppose that I want to model the true distribution is y is independent of x, something like this. And so this is my P star, right? And if I just learned no structure, okay, so this is too few edges, then there is no way that these two variables can model this distribution. There's no way, because for it to model this distribution, you need to have this arrow between these two. Okay, so that's how. So that's what I mean by too few edges. Okay, so there's a lot of things to talk about here. It's only 20 minutes and we're on the third slide. And the good thing about this video is you can watch it in double speed, right? Like, I'll sound like a chipmunk, but at least maybe it's because I'm a bit slow now that I'm going slower. The other reason why you'd like to learn G-star is for something called density estimation. Oops, density estimation. And what is density estimation? As I said before, that's the process of estimating the probability density function, right? And why would you want to do that? Well, to make better predictions, right? To make better predictions over your variables given evidence. So in this case, we want to learn a model which generalizes, right? We don't want a model that has too many edges because it might overfit to specific scenarios of the data. And we don't necessarily want that because sometimes having a sparser network means that we can have improved generalization. Okay, so a simple structure sometimes is better for density estimation. Okay, there are three approaches to structure learning in Bayesian networks. The first approach is called constraint-based methods. Okay, here we see the Bayesian network as a representation of independence assumptions. Okay, and since we're seeing it as a representation of independence assumptions, then we can test for independence between variables that manifest in the data. Okay, so we can run tests, independence tests. We can have a formula which is our oracle, which tells us if two variables are independent given a set of variables. Okay, and if we do that, then we can find IMAPs that best explain the dependence and independence associations. And you've seen an algorithm like this in the very first lecture. Oh yeah, the lecture on Bayesian networks, where we use that PDAG algorithm to discover independence assumptions, or we use it to discover IMAPs of the true distribution. The second approach to structure learning is called score-based approaches. And in score-based approaches, the Bayesian network specifies a statistical model. Okay, so it's no longer just a representation of independencies as before. And so if this represents a statistical model, then we are left with a model selection problem, in which we define a hypothesis space of potential models. So a hypothesis space of potential models, which means that here's an example of something that's in our hypothesis space. Maybe this is a different one, and maybe this is a different one. Okay, and so these are all possible candidates in our hypothesis space. And so we then have a scoring function, so a scoring function which calculates the fit of the statistical model to data. So let's say maybe the fit to data here is 90, the fit to data here is 100, the fit to data here is 20, and then we then search for the highest scoring network. So we look at this one, this is the highest scoring network. No, it's not. This is the highest scoring network. So then this is the model, this is the structure that we choose. So this is a very common approach and a very effective approach to structure learning. It's called score-based structure learning. The final one is the correct way to do it. And I always said the Bayesian way is the correct way to do it. And so in this case, the Bayesian way is this way. But this way is the most difficult way. And here, this is called Bayesian model averaging as approach to structure learning. And this is the best way, as in this will give you the right answer. However, here we see it. We actually look at the Bayesian paradigm as an ensemble, as averaging over an ensemble of possible structures. So in other words, we average out the prediction accuracy across all possible candidate structures. And what this then tries to do is average the prediction of all possible structures relative to the data. And very rarely it can be done efficiently. For some discrete spaces in particular, for continuous spaces, it's much more difficult. Right, so let's start with constraint-based structural learning. So we're going to go through these different approaches in a bit of detail. And for now, let's start with constraint-based structural learning. So this was the first of the methods I showed you. So in this case, we aim to capture the network structure based on the independencies that exist in the domain. And the basic idea here is to use that algorithm that I gave you in that second lecture on Bayesian networks, the build IMAP algorithm, to do this. Okay, so what we then do is we use this algorithm to learn that's the algorithm we use to add variables inside of the network. And before, in the algorithm, we specifically use a set of independence assumptions which corresponded to the true distribution. But obviously, in reality, you don't have that. I mean, it'll be great if we had that. If we had that, we'll just build a network with that. But we don't ever have that. So what we need to do instead is actually look at the data and generate a statistical test to see if that variable is correlated with the other variable. And it turns out that this method works. This is the pioneering method for structural learning in graphical models, and this was the way that causality was used. And this is actually still the model of choice for the learning choice for causality. But obviously, for causality, the best way to do it would be Bayesian model averaging. And that'll be obvious at the end of this lecture, not now. For you, it'll be obvious at the end of this lecture if you don't know anything about structural learning. So the constraint-based structural learning algorithm can be made more efficient by bounding the in-degree. So before, when we were learning, when we were adding variables inside of the network for the build a minimal IMAP algorithm, we didn't really care about the in-degree, but you can restrict the in-degree to be less than or equal to some kind of variable d. So you can pick d to be 4 or d to be 7, and then this will just stop a variable from having an in-degree of 4 or greater than, or 7 greater than. Okay, there's other ways of also constraining the number of variables you condition on, and you can do that. And the other assumption is to say that the structure that you build is faithful to the true distribution, which means that it represents accurately the true distribution P star. So let's see how this is actually done. So this is now we're actually going to be running a constraint-based method to learn the structure of a graphical model, and we need to first we need to define a few things before we start. So the first thing we need to define is this notion of hypothesis testing. So in hypothesis testing, we are testing a hypothesis, and the hypothesis here is that X is independent of Y. Okay, so that's the hypothesis. So the null hypothesis here is that, and this is the null hypothesis, is that the P star, the empirical joint distribution of X and Y, is equal to the empirical independent distribution of X multiplied by the empirical independent distribution of Y. And this just means that these are mutually independent. Mutually independent. This is mutually independent. And if the null hypothesis is correct, that means that they are mutually independent, and we can therefore eliminate the association between them. And if the null hypothesis is rejected, then that means that they are indeed correlated, and we need to leave the association between them, the edge between them. So in other words, we're discovering the empirical mutual information. Now this is a particular way of looking at two variables and seeing if they are correlated, and it's denoted by I of PD, which is the empirical mutual information of the empirical distribution relative to the data. And this is how it's denoted. In this case, it's between X and Y. So we're testing two variables at a time to see if they are correlated or not. And let's now actually look at how this is done. So this formula is a very natural formula. Okay, this formula says that we are basically looking at the ratio of them being correlated, of them being together, which is here. This is the probability of x, y. This is the empirical distribution of x and y, and so is this. This is the empirical distribution of x and y over if they a product of mutually independent variables. So this part here would have been just the empirical distribution of x, and this part would be the empirical distribution of y. So if you look at this formula, it's summing out. It's looking at the ratio of them being correlated over these two variables being independent. And if this is below a particular threshold t, then we accept the hypothesis that they are independent. And if it's above a threshold t, then we reject the hypothesis that they are independent. And when we reject it, we put an association between them. So that's the basic idea. So how do we choose the t? Well, we use a p-value, and that'll be the probability of the data and the data while using this empirical mutual information or whatever metric you're going to do being greater than some threshold given the null hypothesis is true, and the data. So that's the long story short with hypothesis testing. Let's actually look at an example of this. So if I give you a p-value of t, so I say this is your p-value 0.01, and I give you an ordering, then you just use that PDAG algorithm that I gave you in the second slide at the beginning of the course, and you learn the model. So we start off by adding a, so we add a, and then we add b. So what happens when we add b? We've got to have the arrow pointing to b, or everything that existing points to b. So now we're going to test if that arrows actually needs to be there or not. So we use our empirical mutual information. We use the empirical mutual information, which is this formula, and here's our data set here. Okay, so we count up. So for example, I'll just give you a few examples of this. So we expand it for this particular scenario with all of the possible configurations of a and b, and since these are binary variables, this can take a 0 or 1, and this can take a 0 or 1, so therefore you need all possible combinations of them being a 0 and a 1 because it's a multinomial, or in this case a binary. What we then do is, if I want to calculate this sufficient statistic m, a0, b0, then this is the count of the number of times that these are where a is 0 and b is 0. So how many times does that happen? Well, it happens here and it happens here, so it's 2. Okay, so you'll put a 2 here, you'll put a 2 here. How many times is a with 0? And that's going to be 1, 2, 3, so that'll be a 3. And how many times is b0? 1, 2, 3, so that'll be a 3. So you complete all of these and you end up with this. So this is the first expression, this is the second expression, this is the third expression, and then the fourth expression. You then simplify it using your calculator, and you check if it's less than or equal to this value. So you can see here that it's not. It is great. It is greater than 0.014 is greater than 0.1, which means that we must reject the hypothesis. We reject the hypothesis, which means that they are dependent. Okay. And so we put the line between them to say that they are dependent. Okay, so you continue in this way. You do it for C. You plug in the formulas for C, and then you test it. In this case, it happened that C is independent of B, and then you do it again for what is this? The first. So you do this one here for A and C, and it turns out that they're independent. See, and then you do it again with B, C and D. C and B, and it turns out that they are also independent. So that's the big idea. Okay, so what is the limitations then? So we can evaluate independence queries using that procedure that I gave you in the beginning of the course. And when the tests reject the null hypothesis, then we treat the variables as dependent. Okay, so the hypothesis was the empirical distribution of the two for them to be mutually independent. Okay, so this is if we reject this thing, then means that this is not true and therefore they are dependent. Okay, so what's the issue with this method? Well, there's a big limitation with constraint-based structured learning. Okay, since we're learning this variable by variable, right? Then if we make a mistake, right? If we put an edge where there's an edge that's not supposed to be there, we're constraining future edges that are going to come about when we add more variables. And so if you have an error of 95%, so the error is 0.05, we get 1 in 20 rejections wrong. And that's actually chaotic, because if you're making mistakes while building the network variable by variable, then what's actually going to happen is these errors are going to be adding up. They're going to be propagating in a super exponential way, causing lots of chaos and inaccurate paths that could take for future iterations when you're adding new variables in. And that's the big problem with constraint-based structured learning. So it increases incorrect conclusions. The probability of an incorrect conclusion increases at every iteration. And even with a very high percentage like this, 95%, you still get 1 in 20 wrong, which means that when you just added a few variables and you've done 20 independence tests, one of them could have been wrong. All right. So in other words, when we have very few variables, this kind of approach is preferred. When we have very complicated structures with many variables, then we don't generally use constraint-based structured learning. So let's look at a different approach. In this case, we're looking at score-based structured learning. So we're done with constraint-based structured learning. That was our first one. Now we're doing the second one, and then later on we'll look at Bayesian methods as well. So okay, if you notice, I just want to go get some tea. So we're going to talk about, what did I say? We're going to talk about score-based methods. Oh, limitations. Okay, so now I've highlighted the limitations of constraint-based methods. But now we're going to talk about score-based methods, score-based structured learning. This is a very popular approach, popular. And in this approach, we see that we see this as an optimization problem. So if you're familiar with applied mathematics, which is the whole school upstairs, they look at optimization. It's a big thing that they look at. And optimization, it's because sometimes doing the integrals are so difficult, so they actually then leverage optimization tools like Markov-Chain Monte Carlo or other kinds of things to approximate certain answers, and that's the kind of approach that we're going to be looking at for structured learning, score-based structured learning. Okay, so the idea here is that you can score candidate structures using a scoring function, okay, and then search for the graph and the parameters that make the data as probable as possible. In other words, you score candidate structures using a scoring function, and then you search for the highest scoring graph structure with its respective set of parameters. And once you find the highest scoring graph structure with its set of parameters, then you're done. That's basically the procedure, and then you're done. Okay, so in other words, we define now a graph structure, or we can define this concept of a model by the graph structure and the set of parameters that are associated with that particular graph structure. Okay, and we also use for the obviously our best guess of the correct parameters for this particular graph structure would be the maximum likelihood. In other words, the parameters that make the data as likely as possible, and that's our maximum likelihood estimator of the parameters. Okay. I'm having a hard time with my throat. I'm not too sure why. So if I just go silent for a few seconds, just forgive me. I have a cup of tea next to me, so I hope it doesn't cause any disruptions. All right. So to say what I just said more formally, not the stuff about the tea, the stuff about the model and the parameters. To say that a bit more formally and more concretely. What we're trying to do is we're trying to maximize the likelihood of the model relative. So this is a new notation we're going to use. It's called relative relative to the data. So we're trying to find the likelihood of the model relative to the data, and this particular function needs to be maximized with respect to the graph structure, because the model is made up of a graph structure and a parameter, and the parameter associated with that graph. Okay, I hope this makes sense in your head, right? I mean, every time I showed you a Bayesian network in the previous slides, I showed it to you with parameters. Okay, those parameters are optimal, and those are the ones that I'm talking about. So in this case, so the parameters, if we're going to maximize the graph structure with respect to the parameters, then I can actually substitute the model M as this section here, which is just the graph structure and the parameters. And I can then separate the graph structure with the parameters. So you have the graph structure on the outside and the parameter on the inside for this particular equation. And then if I then apply the max for this likelihood on this particular graph structure with respect to the parameters, then I end up with the maximum likelihood estimate, so MLE, that you've seen in the slides on parameter estimation. Okay, so the intuition here behind all of this is that to maximize the likelihood of this, we need to determine a structure that produces the highest likelihood relative to the data. So let's actually see what does that mean. So that's our goal. Okay, so this is not really an intuition. This is a goal actually, because this is the goal that we're trying to set out to do. So how do we do that? Well, we look at two scenarios. The one scenario here is if we don't have any structure, okay? And the other scenario here is if we do have a structure. And if we subtract this one here, A, if we subtract it from B, and if we get a positive answer, positive result, that means that we prefer to have the edge. And if we get a negative result or 0, that means that we're either indifferent or we don't prefer to have the edge. So this is kind of the rationale behind the likelihood score, which we're going to be looking at now. So we can, looking at this model here, GO, we can end up with this equation. So the score of the likelihood of GO relative to the data is the sum over all of the instances. So this is your data. M is an element of the data. Obviously it's the data samples. So for all of M, we find the log likelihood of the parameters for this particular value xm, okay, plus the log of the same thing for y. So in other words, this x decomposes as this y decomposes as this. Okay, similarly, the score of the connected graph, which is the G1, okay, is equal to the log of the value of x, which is this part here, and then the log of the parameter of y given xm, which is this part over here. Remember, this is the p of y given x. So this is what it is. Okay, so we end up with these two equations that describe the two structures that we're looking at. So this one describes that, and this one describes that. And that's basically it. So then what did I say? I said that if we subtract G1 from GO and we get a positive answer, that means that we prefer the edge, and if we don't, then we'll get a 0 or a negative answer. So that's the likelihood score. So then let's actually subtract it and see what we get. So we start off by putting expanding this by this equation here, and we end up with this big part here, and then we also do the same thing for the GO, and sorry, this was G1, and then GO, you get the other one. Okay, looking at this, we see that this one here, if you have this negative here, and this cancels with this. Okay, so we get rid of that. What's left is we're left with this. Okay. Thereafter, we see that we were going over our sum here was all of M. Okay, so this is all of the instances in our data set. But as you already know, we can, from the parameter estimation class, we can represent these as sufficient statistics by saying that we're summing over all x and y, where we have the sufficient statistic for x and y, and then multiply by the parameter value in the particular network. So the parameter value here. And we can do the same thing for the other side. We can say sum over all of the y values, m of y, which is the sufficient statistic for y, multiplied by the parameter of the log y value. Okay, so that's pretty standard up to this point. This part here this log y, where the parameter is calculated. Oops, this parameter is calculated. We all know how it's calculated using the sufficient statistics. So we can calculate that parameter using the sufficient statistics of the combination of the values divided by x, and then also the same story on this side, which gives us the sufficient statistic representation of the parameter for y. Okay, so we end up with this equation. Okay, so far it's looking good, but what's often useful is to represent this. It'll be less compact. I mean, you could just leave it like this and then continue, but a more compact representation will use what we call the empirical distribution. And the empirical distribution is one where the reason why we call it empirical distribution, which is this P of hat, is that it's because it's the distribution that manifests in the data. So it's empirical as in that it comes from the data. And if we we can actually replace this with that, because P of x, P of y, the empirical distribution of that's not supposed to happen. The empirical distribution of y given x is equal to the sufficient statistics of x and y divided by, as you guessed it, the sufficient statistic of x. Okay, so this whole thing here can become the empirical distribution of x of y given x. Okay, this part here, okay, notice that if I just take okay, this was the empirical distribution of y given x, but similarly I can have the empirical distribution of x and y equal to the joint the sufficient statistics of x and y, and then the sum of all of the, I mean, just counting all of the instances. And you all know from grade 3 maths that you can have this equation is the same as this equation, is equal to P empirical distribution of x, y, m. Okay, and so I can just take my what is this thing called, the sufficient statistic, and substitute this guy in there. So I do that, and I then push the m out of the summation because it has nothing to do with the summation. So this m goes out of the summation, which is great, right? Because now I've got something that looks a bit more normal. The same story here. So this m of y is equal to P of y multiplied by m. Okay, and so this one here is just the P of y. Okay, right, so we're making progress. The next thing to do here is move m from here, and then actually take it outside. Okay, so we're doing two things on this step. So the first one is we're extracting m from both summations to take it out here, and the second thing we're doing is we are inserting artificially x here. Okay, and if we do that, if we insert the summation, if we insert x here by our P of y, we have to get rid of the x afterwards. So we're going to sum out x and insert it artificially here so that we can join both of these expressions together. And this works because P, the empirical probability of y, is equal to the sum of x, the empirical probability of y and x. Okay, because this sums out y, it sums out x, and then we end up with P of y. Okay, so the reason why we did that is because now we have exactly the same expression. This expression is the same as this expression. And if that expression is the same as that expression, then piece of cake, right? So we use our log laws and we end up with this here. So this is a pretty cool result. This is saying, I'm sure something must be ringing in your head because you've seen something like this before on the other slide, where you have the empirical probability of x and y and the log of the empirical probability of x and y divided by the probability of x multiplied by the probability of y. So in other words, it's modeling the joint empirical distribution between the two variables over the product of their marginal probabilities, which is the mutual independence assumption between x and y. Okay, so that's really wonderful. And if I have to just then replace this, so if I take all of this just to make it crystal clear in your head, if I have to just take this out here and put in mxy over m, and then here I have m of x over m, and then multiply by m of y over m. Then that looks familiar. Also this part here, see there's the log, and then this will also be mx and y over m. Okay, doesn't this look familiar? Yes, it does. If I go back a few slides, the 80s. Okay, see the same thing, the same equations that we spoke about here on this slide. Okay, this is the same equation. So this is great, right? Because I now have a way of preferring structures as opposed to other structures. Where am I? Here. I have now a way of preferring structures. So this mutual information is the average distance between the joint distribution and the product of marginals. This part here is the product of marginals for x and y. So with a little bit of extra work, you can, instead of looking at just x and y, you can look at x with its set of parents, p1, p2, and p3, and we'll call the set of parents u. Okay, so that's my u. And small u will be the assignment of all of the parents, all possible assignments of the parents. So this equation here that I'm going to show you, which I'm showing you right now, this here is called the this here is the likelihood score, exactly what we did before, but this time we incorporated the parents, not just x and y, but rather all of the possible parents of y, which from the previous one there might have been more. See here, y could have had x, it could have had z, it could have had u, it could have had p, or whatever, and all of these variables need to be represented. We call them u, and that'll be what we use for all possible assignments. Okay, so this part is the mutual information, and it turns out that this part is just the entropy, and because it has nothing to do with the structure, see, it's specifically just for every variable, right? It has nothing to do with the independence associations. Because of that, we often just kick it out and ignore it because it doesn't add any value. It's just a constant. So we often dismiss the entropy term. So this is the entropy term. We can just delete it, and we focus solely on the mutual information term. Okay, so the intuition behind this is that the likelihood score measures the strength of the dependencies between variables and their parents. So before it was just the strength between, well, it was just about having the edge or not having the edge, but now we're looking at the strength of the dependencies between the variables and its parents. So in other words, a higher likelihood score means that we're fitting the data better. Okay, so obviously I just said that, and I'm sure something clicked in your mind, and you must have just thought, oh my God, we are gonna overfit. I'm sure some of you must have just thought about that. There's some very smart people in our class. I'm sure all of you are very clever. We're making it to honors and picking a course like this. So so all of you must be thinking the same thing. So let's look at this. This is a very nice result because now we have a way of choosing graphs. So obviously that means that if I just keep choosing to optimize the score by adding edges in, then I'm going to be doing what I said in the beginning about the problem statement and knowledge discovery and adding too many edges in, and that's exactly what's going to happen, right? So let's look at the limitations of this likelihood score that we just spoke about. So the first one is that it's computationally expensive. Why is it computationally expensive? Okay, so if I ask the question in class, you'll raise your hand and you'll say, it is computationally expensive because the number of dependencies for every variable increases, and that obviously increases exponentially. In the same story, here we go again, and that's the reason why it's expensive, because you'll be calculating that likelihood for a large amount of dependencies. So it's expensive as the number of variables and instances increase. It's also expensive for the number of the size of D, right? D, and getting those sufficient statistics may be linear, but when you've got billions of samples to go through, that is also expensive. So the other thing is that it favors overfitting. Okay, so we always prefer to have more edges rather than fewer edges, and that's what causes the overfitting. So in other words, if x and y are connected like this and there's other variables, it will not stop until it created as many associations as possible. The likelihood score, oh, this one doesn't make sense, but the likelihood score will just keep adding arrows. It'll pick the best arrows, but it'll keep adding arrows until everything is connected to everything else as long as it doesn't. It's acyclic, which is a directed acyclic graph, right? So so in other words, it's going to overfit. It's going to have so many errors, and we're going to have to learn those errors. So it's overfitting. Okay, the other problem is that it learns the empirical distribution, which may not always be what we want. Remember that we're learning the empirical distribution from the data because it's convenient because we have the data and we've got to learn from the data, but sometimes we need to be able to generalize to new instances. We don't only want to learn the empirical distribution relative to the data. We want to also maybe generalize the model to be able to tackle things that it's not familiar with. Okay. So in other words, it may not accurately reflect the true likelihood of the data. The other thing is that different models may have the same likelihood. Okay, so for example, and this is not necessarily a limitation. Sometimes it's a good thing, right? So if so, for example, maybe the likelihood score gives this graph an 80, but it also gives this graph an 80. Okay. That sometimes it's a good thing, and you'll know why later on. But for now, let's just say that that's an inconvenience, because when we're looking for the true structure, we won't be able to identify which is the true structure because everything is giving us the same score with respect to the likelihood score. So coming back to this point about overfitting, the likelihood score will always prefer a more complicated structure to a simpler one. And that's just because of the random noise in the data. So because the data is noisy, you will always get this more complicated score, preferring a more complicated structure. So in other words, the likelihood score won't be happy with this. It will want to add an edge somewhere. It won't be happy with that either. It's going to want to add this edge as well. Okay. And if you have another variable, it's not going to be happy with this. It's going to want to add this edge as well. And then maybe it's going to want to add that edge as well. And then maybe also it wants to add this edge too. So it's always going to prefer more complicated structure, which means that the output, if you just let the likelihood score have its way, it's going to give you a fully connected graph. And here we go again, chain rule for Bayesian networks. Right, so that's great. Now we covered the likelihood score. So now you know how score-based structural learning works, somewhat, because I didn't show you how we look for the highest scoring network yet, but I did show you how what mechanism do we use to score the different structures. So I promised that I'd show you what Bayesian model averaging is all about. So I'm gonna kind of show that to you by talking about the Bayesian paradigm in structural learning. So it sounds like I'm just stopping score-based structural learning and then starting something new, but in actual fact what I'm doing is I'm showing you how do we use Bayesian model averaging to come up with a really cool score which allows us to incorporate into score-based structural learning. So let's then go back to the basics. Back to the basics means the Bayesian paradigm. So what is the Bayesian paradigm in terms of structural learning? So looking at this equation, I have shown you exactly what do we mean by being Bayesian when picking a score. And here we're saying that if we want to calculate the probability of the best scoring structure given the data, okay, then we need to model the probability of the data given that structure, multiplied by the prior probability of a structure, okay, and then divide that by the probability of the data. So in other words, you're finding out the structure, the correct structure relative to the data by finding the most likely structure, by considering the likelihood of the data given the structure, multiplying that by a prior choice of structures. So what would you like to focus on? And then divide that by looking at all possible configurations of the data. So this is nuts, all right? Especially this one, looking at all possible configurations of the data. And because the data here is independent of the structure, we often ignore it because we don't actually model it. You could, but we don't, because we don't because it has no association with the structure. So it's easier just to ignore it. But I mean, a PhD student can easily pick this up and say, well, what can we do here? What can we actually look at when we're doing structural learning by incorporating different kinds of data samples or different kinds of structures of the data or whatever? This is averaging over all possible data samples, right? So it's really great. It's a proper Bayesian way to look at this problem. But anyways, for the sake of this lecture, I'm going to just cancel it, and we don't look at it. So let's actually, it's always sometimes useful to look at the log, because then we get additions instead of multiplication. So let's look at the log of this Bayesian score, looking at the probability of the graph with respect to the data. So the Bayesian score this is how we denote it, the B score, okay, is equal to this part here, which is the likelihood of the data given the structure. And then it also adds to it this part here, which is the prior. And this prior allows us to be able to specify some preferences over the structure. Okay, so let's look at this in a bit more detail. Okay, so we'll look at each of these things in detail, but we're looking at this first. So we'll look at this one later, right? Later. So let's look at this one first. So here we're looking at the probability of the data given the graph. Well, I told you what the G is. The G is the M. It's the model. So there we're actually looking at the graph with respect to the parameters. And we're going to integrate over all possible parameters. All possible parameters. I know, right? All possible parameters for this particular structure, G. We're looking at for all possible parameters. So now it's no longer the maximum likelihood. Okay, now we're looking at something called the marginal likelihood. So for all possible parameters, you have the probability of the data given those parameters in the graph structure multiplied by a parameter prior. And this parameter prior is the probability of the parameters that you pick given the data. So this is now, this slide is perhaps the most important slide in structure learning, because it shows you how we should be doing it. How we should be doing it, but this is the most difficult way of doing it. So if you can do it this way, then it solves causality, it solves all of the other problems we have, because it kind of has, it gives us a way of discovering structures using a Bayesian principle. But of course, this is the most difficult way of doing it. But the good news is that you'll see, I'll get to a point of these slides where I'll show you that we can approximate these scores using something called the BIC score, and I'll talk about that later on. Okay, so I think I'm realizing that this is a bit of a difficult lecture, but maybe it isn't. Maybe it's just that I'm too close to the work. Maybe you're looking at this for the first time and you're like, oh wow, this is so interesting. This is so fascinating. And I'm gonna study this in my PhD with Professor Judah. Okay, so let's go back here, back to this beautiful slide. I think I'm gonna print this slide and stick it on my wall. This is the part I want you to look at now. It says that we're looking at the parameters of G, but but I told you that in the Bayesian paradigm we don't look at the MLE. We don't look at the maximum likelihood estimation. Okay, because that's the wrong way to do it. We must look at parameter estimation using a Bayesian principle, especially when we're considering different structures. So I'm going to show you the difference between doing this using marginal likelihood, which is what this slide talks about, okay, marginal likelihood, as opposed to doing it using maximum likelihood, what you know so far. So you don't know what marginal likelihood is yet, you only know what maximum likelihood is. So let's compare these two things and see what we get. So both of them are calculating the likelihood of the data relative to the model. Okay, both of them are doing that, but maximum likelihood calculates the maximum. It's the maximum, it's the parameter value that makes the data as likely as possible. On the other hand, we can look at the marginal likelihood, which calculates the average with respect to the data, with respect to the model. It calculates the average parameter value with respect to the model. And yeah, okay, so that's kind of it, eh? So the Bayesian approach models that this parameter is not the only choice. Okay, there are other choices. Right? The MLE is just one possible choice of parameters. And so then integrating over all possibilities of the parameters allows us to measure something called the expected likelihood. So we're not so worried about maximum likelihood anymore. We're now worried about expected likelihood. And this is the right way to do it. Okay, so what is the difference between marginal likelihood, which is this one here, and maximum likelihood, which is this one here. Okay. So marginal likelihood and maximum likelihood. So let's look at the example. So here I ask you the first question, calculate the maximum likelihood of the data. So the likelihood of the data, I'm not asking you to calculate the parameter value. I'm asking you to calculate the likelihood of the data, the maximum likelihood of the data. Okay, so how do you do that? Well, how do we denote that firstly? So it's the probability of this data, okay, given the maximum likelihood parameter. So the maximum likelihood parameter is given to us. So let's say that the parameter, maximum likelihood parameter is how many, what is the probability of a square? The probability of a square is, so the probability of, I'll just put a little, it's a weird notation, but let's just put it as probability of SQ and as a CI, right? So circle and square. So this becomes, the probability of a square is 1, 2, 3. There's 3 out of 5 things here, so we're going to do that. And the probability of a circle is 2 out of 5 things, okay? So then the probability of the data given the maximum likelihood parameter is equal to, it's the parameter value for the likelihood of a square, for the maximum likelihood of a square, and also this is the parameter value of the maximum likelihood for a circle, and this is the number of times the square appears and the number of times the circle appears. So let's write it out. It becomes 3 over 5 multiplied by 2 over 5, so that's 3 over 5, 2 over 5, multiplied by 3 over 5, multiplied by 3 over 5, so that's these two here, and then multiplied by 2 over 5. So we can summarize this as 3 over 5 to the power of 3 multiplied by 2 over 5 to the power of 2, which is 108 divided by 3,125, and that gives us about 0.037. So this is the likelihood of the data. On the other hand, I can ask you to calculate the marginal likelihood of the data. Right, the marginal likelihood of the data, we calculate that with a parameter prior, and we're gonna use a Dirichlet prior for this, which will be a prior for the squares and a prior for the circles. So we can just name, maybe this will be for squares and this will be for circles. So how do we calculate the marginal likelihood? Well, before the maximum likelihood, all I had to do was just basically multiply the parameter all the time. But in a marginal likelihood, we want to calculate the probability of the data, the sequence of data. There's a sequence. And we start off with the first sample, and then we do the second sample, and then with the third sample, and so on. And that joint probability of the data instances, x1 to xm, can be summarized using the chain rule as well, the chain rule for probabilities. So we calculate firstly the probability of the first sample. Then you multiply that by the probability of the second sample you see, given that you first saw the first sample. Then you multiply that by the probability of the third sample, given that you've seen this sample and this sample. Then you calculate the probability of this sample, given that you've seen this one, and this one before. So we're doing it sequentially, and eventually you'll be calculating the probability of the last sample, which was xm, given the first sample all the way to the m-1 sample. So that's the correct way to do it. So let's actually see. So let's model this as an equation, and it turns out that there's a very natural equation that falls out of this. And this is the probability of x m1, which is observing the next instance. Okay, so the mth one plus 1 is equal to a square. Okay, so this is for the probability of the mth plus 1th instance being a square, given all of the other data that you've seen previously, that is equal to the prior for squares plus the number of times you've seen a square. Yeah, so that's the number of times you've seen a square in the m examples that you considered. Okay, so your m to the power of m of 1 is for squares, and then m to the power of m of 0 is for circles. Okay, so this m to the power of m1 is the number of squares that you've seen in m examples. Okay, so the mth plus 1 square, we use the m examples to calculate. So let's see this in action. Let's look at this actually in an example. So the probability of, so just as like we saw here, the probability of all of these samples using the chain rule, the joint probability of seeing those samples. Okay, because we haven't seen any instances, any squares yet. Okay, the first one is a square, but we haven't seen any squares yet. So remember, we're looking now at the mth plus 1, and we need to consider the mth sample, but we only seen the first square, so we haven't seen any squares before that. So then here we would have had plus 0, because there wouldn't have been any squares before that, divided by the prior, which is now alpha. So alpha will be alpha 0 plus alpha 1, which is equal to alpha, and that's alpha. So then you multiply that. The next thing you're seeing is a circle. Have I seen any circles before this one? No. So I put a 0 there. So it's the prior for circles plus 0 divided by the prior alpha plus 1 plus m, right? So I've seen, I'm now on the second sample, my m is equal to 1, in other words. Okay, then you multiply that by the third, we now saw a square. Okay, so it's the prior for squares. Okay, so I see, so actually it looks like my theta O is for squares and my theta 1 is for circles. Okay, sorry about that, I didn't want to confuse you. So this is for squares, and that's why it was a square. This is a circle, this is a square, this is a square, this is a circle. Okay, anyways. So I was here, and I did see a square before, so that's why I put a 1 here. Okay, so it's squares, the prior for squares, plus, I saw 1 square before, divided by my total alpha plus 2, because 2 is my number m. Okay, and then you multiply that by the prior for circles, and sorry, the prior for squares. I'm now here, so we have the prior for squares plus, I saw 2 squares before, so I'm here now. So I saw 2 squares before, 1 and 2, and that becomes my 2, and then I got alpha plus 3, because 3 is my m. Multiply that by circles, which is here, alpha 1, which is the prior for circles, plus, I've seen 1 circle before, here it is, and that will be the 1, alpha plus 4. Okay, I hope you understand this. I'm going to take my markings away. And that's basically the idea. And so you put all of these together, and you organize them nicely. You put the squares on this side, okay, and you put the circles on this side. Okay, and then you end up with a very nice equation. And if you pick your alpha 0 and alpha 1 to be 1, then obviously your alpha will be 2, because you're adding those two together. Then you can actually substitute stuff in here, and you can end up with this. So the marginal likelihood is 0.017, and the maximum likelihood is 0.035. So we see the marginal likelihood is less optimistic about the likelihood compared to the maximum likelihood. Okay, so it turns out that, as I told you, the maximum likelihood models a higher probability to the sequence than the marginal likelihood, and which means that it uses an over-optimistic view of the likelihood, of the log likelihood. So the maximum likelihood uses a hindsight optimized parameter for the entire sequence fit. Yeah, which is problematic sometimes, right? Because you don't want to dismiss the sequence. I mean, the sequence might be important, and the marginal likelihood takes that into account. So the general binomial distribution with priors, so this was the formula from before, and you've seen that we can actually get this kind of equation from grouping them by squares and circles. So this was the squares, that was the circles over m. And I'm sure you've noticed there's a pattern there. You had alpha, and then what else? We had alpha, then we had alpha plus 1, then product alpha plus 2, alpha plus 3, alpha plus 4. Okay, and then here at the top we had 0, and then 0 plus 1, 0 plus 2, prior plus 1, prior plus 2, and then the prior for circles, prior plus circles plus 1, prior for circles plus 2, and so on. So there was a general pattern. So we can see that the general binomial distribution with a beta prior looks something like this. And it turns out that this can be represented very nice using something called the gamma function. And the gamma function will basically represent these aspects. So I've highlighted how you can use the gamma function to represent the blue part of the equation, the red part of the equation, and the orange part of the equation. What's also really nice is that I showed you that for binomials, but now look at this. We can also extend this for multinomials. We can extend this for multinomials where this particular distribution, the same as before, is equal to this will be the denominator part of it, okay? The denominator part here, which was this part here, okay? And then we have the numerator part, which can be a whole lot of things. It doesn't have to be circles and squares. You can have circles, squares, triangles, as many i's as you like. It can be a quantile k, or as many values as you want, which makes this useful for multinomials. So that means that this will just expand, right? So if you take k to be equal to 2, you end up with just getting squares and circles, okay? But you can take k to be anything, and you can have many different values in the numerator divided by the denominator, which will generalize out the sequence likelihood. Okay, so that's extremely useful. And also notice that the maximum likelihood estimate, MLE, uses sufficient statistics, and the marginal likelihood also uses sufficient statistics. I suppose MLE, they both have the same abbreviation. This is the maximum likelihood and the marginal likelihood. And so they both use sufficient statistics, which is really convenient, because then we can actually be using the same language here to compute things. Okay, so that brings me to the Bayesian score, which is now looking very scary if I look at it like this. I've been working with this equation for years, and now when I look at it on this slide, it looks extremely scary. But if you go back here, things are safe again. Okay, so I'm not going to go into too much of detail here, right? But all that this is showing you is the generalization of what I've just shown you. It incorporates the marginal likelihood for the graph structure. So this just incorporates the marginal likelihood with G. So before we weren't really talking about G, okay? This incorporates G, and G has nodes X, which has parents, assignments UI, and so on. So this big equation here just gives you a score for the probability of the data given G. And this is not actually that scary, because you can just plug it into a calculator and it'll give you the right answer with the gamma function. And every computer nowadays can do it, right? Every computer nowadays has a gamma function built in, and so you can just plug it in and it works. So, I'm not going to ask you to recite this. I think this is on your formula sheet, but you're not really going to be using this formula. What I'd like you to do is just understand some basics about it. You don't have to walk out of this course knowing this thing off by heart or knowing exactly its properties or whatever. I'll show you the averaged properties in the next couple of slides. But this is for those who are interested in maybe one day becoming a graphical models person. This is something that you should know, and this is called the Bayesian score. Of course, like I said, this I can leave this for more advanced class, but it really isn't difficult. If I have to just explain it, it's pretty straightforward. Okay, so I'm going to just leave you with the properties. Okay, right. So the Bayesian score is biased to simpler structures, right? So it likes simpler structures, but if it gets more data, right, as the data approaches infinity, then it recognizes the need for more complex structures. But it doesn't want to use complex structures because it doesn't want to overfit. The Bayesian score is a very nice score. And because it uses the Bayesian paradigms, right? Occam's razor and everything else. So it wants a simpler structure, and it's going to try to design a simpler structure. But as it has more data that it can support the need for more complicated relationships, then it'll recognize the need for a more complex structure. So the beautiful property of the score is that it trades off the fit to data with the model complexity, and therefore reduces overfitting. It turns out that there is a very nice approximation of the BIC score, so of the Bayesian score. So this is the scary Bayesian score that I told you that you can know some of the properties about, which I've told you about the properties. But there's an approximation of the score, and that's called the BIC score. And it looks, oh, when you look at this, it just, you just look at it and you feel happy, because this is what we know already from the previous slide, the mutual information. The mutual information, right? So we feel happy. I draw a happy face. Okay, there's the mutual information. And what else do we recognize from here? Well, there's some simple things: the number of instances. You got your n, the number of variables. So in other words, the BIC score is the mutual information of every node and its parents. Okay, every node and its parents, minus so this is a more local thing, okay? But now we're minusing the log of the dimension of the model. So minus log of the dimension of G. So which is, well, this is the only thing you don't know what it means. This is the number of independent parameters. Number of independent parameters. Okay, so that's the number of independent parameters. The dimension, okay, and I showed you what it means to have an independent parameter from the first. In fact, you had a tutorial on it as well. Okay, so this is the BIC score, and this you'll find it's the best. It's the best one. It's the best one because it incorporates Bayesian principles. So we always prefer the Bayesian information criterion to the likelihood score, say. If you negate this equation, you get something called the minimum description length, it's very much used in coding, Shannon's principles, and so on. And that gives it's information theory. It has some benefits in information theory. So it's kind of the same score. You just negate it. An important property of the score is that this mutual independent mutual information term grows linearly, okay, and this part here of the equation grows logarithmically, okay. So it doesn't want to prefer, so the mutual information term grows linearly and the complexity term grows logarithmically. So you can think of these two parts of the score as this one here is the likelihood. This is trying to fit as many edges as possible to make the data as likely as possible. And this part here, it doesn't want to do that. This one wants to reduce the complexity. It wants to penalize the likelihood. See, penalizing. This is a negative. It's minus. Okay, it's penalizing the likelihood score to bring it lower. So if you have a very high dimensional, and the number of independent parameters are huge, then the penalty for this term will be huge, which this part here will be very high, and it will bring down the score value. And obviously we're trying to maximize the score here, so if you bring down the score value, then we won't prefer that structure. So that's something important to remember. This is the beautiful property. So this is growing logarithmically, and this is growing linearly. Okay. So obviously, given that this is growing logarithmically, the more data you have, the more emphasis will be placed on the fit to data. Okay, remember it's growing like this with the number of data samples. So this is your M. The more data you get, the more emphasis is placed on the likelihood, and the less is placed on the dimension. Okay, the likelihood continues to grow, and so on. Okay. All right, I hope that helps you. So this is a nice graph that just shows you what I just told you. So here you have M, the number of samples, being the x-axis. And then here you've got the score. And we're trying to now see what is the trade-off for the fit to data versus the model complexity. And we see that as you have more samples, then there's a trade-off that happens. We rather prefer to have more fit rather than we prefer to have more complex structures as the number of samples increase. Okay, so that's wonderful. That's really wonderful. So I think I'm realizing more and more that this particular lecture is quite difficult, which is the real reason why I asked you to choose whichever lectures you want to do for the exam, whichever topics you want to do for the exam. So between particle-based inference, parameter estimation, structure learning, causal graphical models, and structured decision problems, you pick 3. Okay, pick 3 of those topics, and you can write the exam on those 3 topics. Okay, it doesn't have to be this one, although I would pick this one. This one is very exciting, isn't it? But to give you a taste of what kind of questions I ask you, I will ask you. I did give you an exam. I gave you an exam to look through as well so you can pick, so pretend that you're writing the exam and then pick any of the 3 topics. For honors students, for master's students, you got to pick 4, unfortunately, because you need to have some extra skills at the end of this. So you pick one more topic. So honors students can pick between particle-based inference, parameter estimation, structure learning, causality, or structure decision problems. You pick whichever one you'd like, any 3, and then the master's students can pick any 4. Okay, so I intentionally made these a bit difficult because I want you to specialize in a field that you are passionate about. And maybe, if you want to do a postgrad or a master's or PhD, then at least then you've already started thinking about the methods that you want to look at in more detail. You started thinking more seriously about those methods, and that's why I have asked you to do it this way. But obviously the bread and butter, so test 1 was all the bread and butter that you needed to know. There's all of that Markov networks, Bayesian networks, exact inference, and so on. There are stuff that's non-negotiable. Those were learning outcomes that you had to have. Okay, let's continue. So this was all of that stuff about the likelihood score and the Bayesian score, BIC score, and whatever. But now the Bayesian score also considers a structure preference. It also considers a preference on priors, which is the structure preference that you can have. So there's lots of ways of doing this. This here has a constant influence. It has a constant influence on the score value itself, okay, which means that it has a minor influence. So it has a minor influence on the Bayesian score. So this could have been the BIC score or whatever, but here, which it grows linearly or whatever, but this one here just is a constant. And because it's a constant, it has a very small influence, okay? But except for when you have very small data sets. When you have very small data sets, then this here really helps out. When you have a large amount of data, then this becomes negligible and this takes over. Okay, so that's the beauty of the Bayesian score as well. You can leverage on when you don't have much, you can still have a decent model. Okay, so yeah, okay, so what kind of things can you choose, right, for this? Okay, you can choose, you can have some kind of value for the number of edges. Okay, so for example here, so you can, in this particular prior, you have the probability of G, which is this part here, and C is a small value which is less than 1, which means that as you increase the exponent of C, you get closer and closer to 0. Okay, and this prior here just looks at it looks at a small, if you have a lot of edges in the graph, then it doesn't prefer it. So it's also like a penalty term. So it has a smaller influence. It adds a smaller value if you have a very complicated structure, and if you have a very simple structure, then the exponent will be very small, and therefore it will actually not bring down the score as much. It's useful for these priors. So this was an example of a prior, right? There's so many examples that you can think of, but it is useful for these priors to satisfy something called modularity. Okay, and structural modularity is very much about being able to calculate your structure prior by segmenting the graph structure. So, for example, here, this particular prior here that I've told you about, you can calculate it easily by just counting edges at a local level. So you count the edges per node, and then that becomes modular. It becomes modular. Okay, so that's kind of the big idea, right? So here, see, it's the product of the probability of each of the parents of X. Okay, so that's kind of what we want to do. We want to look at X, look at all of the different X's, and look at the parents, and then calculate the structure prior that way. So that's a very useful property. Why is it useful? Because it relates to something called decomposability, which I'll talk about next. Not now, but in the next couple of slides. Okay, all right. So what's also useful is to make all the I equivalent network structures have the same prior, and that's because we're going to end up in a situation where structures that have the same likelihood to the data should give us the same score, and we call that I equivalence. We want our scores to be I equivalent, and if your prior is adding noise to that, we won't be able to recognize which graphs are I equivalent. So that's why it's important for structure priors to be able to score I equivalent structures the same. So that's great. We're going through the whole Bayesian stuff here, which is really wonderful. And there's one more thing to talk about. So this marginal likelihood stuff from before, we spoke about it, and we now know how to calculate it using the Bayesian score and the BIC score, and we also spoke about structure pliers. Oh, okay, I'm getting tired. And but we haven't really spoken about parameter priors. So we spoke about structure priors on the previous slide, but we haven't spoken about parameter priors. And there is really two ways of thinking about parameter priors. Number one, you could pick your alpha like we did before. Right? The K2 prior is just one that uses a Dirichlet prior. But this is exactly like I've shown it to you. You pick the Dirichlet prior. In the parameter estimation class, I showed you how to pick a prior alpha, and there you would pick the prior. That prior will be equally distributed for the whole CPD or whatever, and then you basically use that. But it turns out that doing that in the context of structural learning can sometimes double count priors, because remember, you're counting it based on the structure, and the structure has certain properties which causes some priors, some alphas to be stronger in certain contexts than others, and that now causes an issue with when you add it to the marginal likelihood. So that's not always a good idea. So the K2 prior has its place, and sometimes it doesn't work very well because of this double counting evidence, double counting priors. But a better way to do it is to rather, instead of putting a prior inside of each of the parameters, right, rather put a prior over a probability space. So you can specify a prior for a particular setting of xi and its parents by giving us a distribution. So this P prime is a distribution, and putting that distribution prior over the probability space, and doing this will allow us to bypass the parameter and rather offer a more holistic prior which we can easily reuse. So we've spoken about a lot of different scores. We spoke about the AIC score, we spoke about the BIC score, we spoke about the likelihood score, we spoke about the Bayesian score, we spoke about the K2 prior, the BDE prior, BDE. We spoke about the BDE prior and so on and so on. There's lots of stuff we spoke about. But there are important properties that our scores, for it to be useful, for us to pick the scores that we want, we need to have some properties. So let's go to property number one. The first property I'm going to talk to you about is consistency. It means that the true structure in our space will always give us the highest score. Okay, so that's consistency. So if our score has this property of consistency, then it will always give us the highest score that it will ever give us will be the one for the true structure. The second property here is that of decomposability. And decomposability is a very nice property, especially from the context of computational savings. Okay, and here we're saying that the score can be broken up as a sum of family scores, which means that if I have a network like this, okay, then I can score this network in segments. I can score this part first, get a 30 here, then score this one with respect to its parents, then score this with respect to its parents, then score this with respect to its parents, and then I add up all of those scores. So 50 plus 10 is 60, and you add 30, 60, 70, 80, 90, plus 20, 190, 100, 110, so that becomes 110, and then this will be my total score for the entire network. If your score can do this, if it can compute its score as a sum of family scores, Then it has a property called decomposability. And this is extremely important for computational savings, as you'll see later. You'll see later why. So, so scores like the BIC score and the likelihood score are decomposable. Scores like the BIC score and the Bayesian score are consistent. And I'll just leave this as a question. Do you think the likelihood score is consistent? Do you think that the likelihood score will give us the highest score for G star? Yeah, and I'll leave you to think about it because it's not such an easy answer, right? And yeah, you can go and figure that out. It'll be a nice exercise for you. Right, so that's decomposability and consistency. So tick and tick. Likelihood score. So these scores are all score equivalent. And what does score equivalent mean? Well, score equivalence is the stuff I was talking about earlier. It means that networks from the same equivalence class will have the same score. So if networks from the same equivalence class, like for example, let's say these are I equivalent. I have shown you this example many times. Okay, so here we have the arrows are going down here, and the arrows are going down here, and then the arrows are going down here. So these are all I-equivalent structures. They all encode the same independence assumption, where this is Z, Z, and Z, X, and Y, X, and Y, X, and Y. Okay, all of these encode the independence assumption X is independent of Y given Z. Okay, this is all of them satisfy that particular independence property. And so all of these, if the score gives us, if the score that we use, like likelihood, BIC, BDE, and so on, if they all give us the same score, like maybe this is 30 and 30 and 30, then we say they are score equivalent, that the score is score equivalent. Okay, right, so let's put now, this is when you pause the video and go have some coffee, because now we're going in a different direction. So up to this point, right, I told you what score-based structure learning is. It was about developing a score, and we looked at lots of scores, okay? Lots of scores. And then after that, after we develop the score, then we need to now use the score to find the highest scoring network. So now that's what we're going to look at now. We're going to look at finding the network using the score. So now at this point, we're going to assume that we've got a score. I'm not going to specifically talk about a score. Okay, so you pick any score you want. We have a score. You can even invent your own score. It doesn't matter. If it has those properties like decomposability and score equivalence and consistency, that's going to be really useful. But I'm going to assume that you have a score and you've picked it. So now we're going to actually use that score to find the graph structure that we want. So we've got upstairs in applied maths, they're going to be very happy because we have what they call a well-defined optimization problem. And here we've got a training set D, so that's our data. Okay, we've got a data set. We've got a scoring function that can be the BIC score, the AIC score, the likelihood score, blah, blah, blah. Any score you want, and including priors. You can have a prior, a Dirichlet prior, the K2 prior, the BDE prior, any prior you want. Okay. And also we have a set of network structures. Okay, so you got a set of network structures. So here's one structure, here's another structure. Okay, here's another structure, here's another structure. Lots of structures, so many structures. How many structures? You tell me, how many structures? How many different structures can you have? Super exponential. Okay, lots and lots of structures. And the output of this optimization problem is the set of I-equivalent structures, all of the ones that maximize the score with respect to the data. So in other words, the highest scoring network structures. And why are they structures instead of structure? Why is it that we're going to find many and not just one that optimize the scoring function? It's because that I told you many times, and in a previous slide I showed you that you can have situations like this where you have different structures that all optimize the score, that give you the same score. Okay, right, so let's start with a simpler problem, the simplest problem that you can consider. So here we're going to learn a tree. Okay, we're learning a tree. So there are many advantages to learning trees. So here we're not going to look at learning graphs just yet. We're going to first look at learning trees. Why would we want to learn a tree? The first reason is because they can be learned very efficiently. They can be learned in polynomial time. So the complexity for structure learning, I'll tell it to you later on. But for now, all you need to know is that trees are much easier than that. It can be learned in polynomial time. They are very sparse. I mean, a tree is sparser than a graph by definition. A tree only has at most one parent, and a graph can have many parents. Every node can have many parents. So they are sparse by definition compared to graphs, and therefore they avoid overfitting. Okay, so they generalize very nicely. What else? They capture the most important dependencies. Okay, so the most important dependencies between node by node in pairs, those are the ones that are represented in the tree. And so that's very useful, because then that means that maybe capturing that summative information can provide domain insight that captures the most important associations. So maybe it's not going to give you the most important group associations, but it's going to give you the most important associations in terms of pairs of variables. Pairs is in just one or the other. The other thing that trees are useful is that they provide priors for other more complicated graph structure procedures. So later on, we're going to look at more complicated graphs when we look at learning graphs here at the bottom. Okay, it's not letting me circle that. But in that case, we do want to be able to use trees as a prior. So it uses priors, and yeah, also when we're doing density estimation, if some of you do your masters in graphical models or PhDs in graphical models, sometimes in particular if you're doing it in structure learning, then having a tree is a nice baseline to show that your graph algorithm is performing better than a tree, which is a useful thing to do because a tree is the simplest case of structure learning. So how do we actually learn a tree? So assuming that we have a particular scoring function, then we can easily just learn a tree by calculating a weight between I and j. Okay, and this is very easy if you have a decomposable score. Okay, because if you have a decomposable score, then you can isolate the score for just the variable and then the parent that we're considering for that particular variable. So we consider a weight from I to j, and then we calculate the family score of that particular variable I and its parent j, and then you subtract that from x of I. And why do we do this? Because if we get a positive value here, that means that this was higher than that, and that would mean that if that is higher, if this left hand side is higher than the right hand side, therefore it's positive, and we prefer to have the edge there. And if it's negative, then we don't necessarily want to have the edge there. Okay, so we have a positive correlation or a negative one. Okay, so if the score is score equivalent, then I think it goes without saying that if we have this property, then the weight going from I to j will be the same as j to I, right? In other words, if it's score equivalent, then this will give you the same as this. Okay, so this will give you the same score, which is useful as well. So how do we do this? Well, to learn this tree is very simple. All you do is, so suppose that you have variables a, b, and c. Okay, just three variables, and we're trying to learn a tree between these three variables, and a, b, and c. Okay, I'm representing the tree here, the tree as an adjacency matrix. And the way we do that here is we're just going to say, okay, let's calculate the weight from a to b. We get a number here. I'm just going to do that. Then a to c, then you do that. Then b to a, you do that. B to c, you do that. C to a, you can do that, and then c to b. And so, I mean, you would expect if the score is score equivalent, you would expect it to be symmetrical about the diagonal, right? But if it isn't, you should be open to the possibility that it's not going to be, because not all scores are score equivalent. And so you can then, once you have this, having calculated the scores between all of the nodes individually, then you can use something like Graphical or Prim's algorithm to calculate the minimum weighted spanning forest. Oh, sorry, the maximum weighted spanning forest, because you're trying to maximize the score. And so calculating sufficient statistics using our table here, will be n squared multiplied by m plus learning the maximum weighted spanning tree, which is going to be n squared log n. Pick any algorithm you want. You can try Prim's algorithm or Kruskal's algorithm, and they give you similar complexities, and they work. They use different kinds of strategies to find a random forest. A forest. Yeah, and that's basically it, right? For the likelihood score, you would expect this always to be positive because it'll be positive just due to noise in the data, and the BIC and the BDE score can be negative as well. So you should prepare for that, and depending on whether it's negative or positive, you can try different things. So that's the basic idea behind learning trees. So that's done now. We're done talking about trees. Let's now talk about graphs. And we always start in this course with the problem statement. And this is now a very big problem, but it's a big problem, but it's it doesn't stop us from actually doing any work. So the following problem is NP hard for any degree greater than 2. Finding the structure that maximizes the score from a set of candidate structures and a dataset D is NP hard. Okay, and this is intractable. So this is finding the right answer is sometimes impossible. However, we resort to heuristics. So this becomes a heuristic combinatorial optimization problem. And again, we refer to our people upstairs in applied maths who study these things every day, and they can also help us to calculate some new scores. The field of applied mathematics has made enormous contributions to these type of problems, and that's why computer science and applied maths, I think they belong together, because a lot of the fields are they're all very much related. Computer science and applied maths. Yeah, it's great. I mean, before the school used to be computer science, and this is when I was a student, and then we had applied maths, which was a different school altogether. But in computer science, we were having lots of decrease in staff numbers, and the school wasn't under sufficient leadership, so the school was dwindling, and applied mathematics came in and assisted us restabilize the school. So we restabilized the school with the help of applied maths, and then we ended up with Kazam. And so computer science and applied maths are brothers in many ways, and now our schools are merged together. And I think this slide here is a great reason how we can actually have collaboration between our schools, because sometimes it is difficult between computer sciences and applied maths. But maybe if you do your master's and PhD in graphical models, I feel like that's becoming my motto now. If you do your master's and PhD in graphical models, maybe you can actually work in both of these fields, which is wonderful. I'm a computer scientist. I've never done applied maths stuff, but I had to learn these things on the fly. But even from a very naive evaluation, these fields are very much looking at the same kind of problems, just through different lenses. Okay, where was I? Great. So these are injectable, right? So the heuristic method that we're talking about, it defines a search space, a scoring function, and a search procedure. So let's look at all of these things together. So if we start off with a search space. So a search space. So when we're looking at a search space, then we are considering all the different ways, all of the different structures that we can actually consider. So let's look at only 3 variables. So we have this one here. Here's a possible structure. Okay, let's look at 4 variables. Here's a possible structure. Okay, now with these 4 variables, what other structures can I have? Okay, so let's say we add an edge. Okay, I can add an edge from this graph here. And where can I add that edge? I can add the edge from here to here. Okay, I can also delete edges. So I can remove the edge, this edge from here to here. Okay, so I could have added an edge, I can also remove an edge. Okay, so I've taken out this edge. I can also reverse an edge. So I can take from here, reverse. Okay, and there I now reverse the edge from here to there. Okay, and so now I've got a new, so just with these 4 variables, I can see there's lots of different ways that I can change these graph structures. So I can delete edges, add edges, and these are all called operators. These are called operators. A better way to visualize this is in an adjacency matrix. So you can have A, B, and C, A, B, and C, and you have something like this. And that's just, you can't have an edge to itself because that'll create a loop and that's not allowed. So let's see, you can have, so if you have an edge, so the T is saying that the edge is there, so that's T. And so removing an edge will just be to take out T, okay? Adding an edge will be to put a new T in. Okay, and obviously we must always check to see if the graph is DAG, a directed acyclic graph. It must be acyclic, okay? Because it's a Bayesian network, has to be acyclic. Looking at it this way also, it's easy to understand why I say the search space is n squared. Because it will take n squared operations to completely change the graph from one part of the search space to the next. Okay? So that's really nice. Okay, great. This is a nice way to visualize it. So the properties of the search space is that the diameter of the search space can be n squared if you have these operations. Is it exactly n squared? It's actually 3n squared because you have these three: addition, deletion, reversal, those possible things that you can do. Obviously, to get from one end of the search space to the other, you have to delete all the nodes and then add new nodes in. Okay. Not nodes, or add new edges in. Okay, and the other property is that these are local operators, which means that they change. They have local changes to the score. So if you, for example, here when I went from here to here and I removed an edge, okay, everything else was the same. For a decomposable score, if this was a 10 and this was a 20 and this was a 30 and this was a 40, and my total, if I sum this 40, 50, 60, 70, 80, 90, 100, this is 100, right? When I remove this edge over here in this graph here, okay, the only thing I changed was this 40. Taking this edge out here changed the 40 to maybe a 30, which means that everything else remains the same. So the 20, the 10, the 30, and the 30 remain the same. So that's 60, 70, 80, 90. So this means that this will still be the same, this will still be the same, this will still be the same, but this now changes to a 30 from a 40, which means that the total score, it was local changes that caused the score to change. And that's, like, as you can imagine, is very useful. So there's different search procedures that you can use. And now that we have a search space, we can actually look around in the search space for the best procedures. And one of them is the greedy hill climbing procedure. Okay, so the greedy hill climbing procedure is a very simple procedure. So we pick a starting point. This can be a tree, it can be a prior that you select, it can be anything. It can even be a random graph. You compute the score of this particular graph that you're starting off with, or tree or whatever. Okay, then you list all of the neighboring structures from this graph T. So you list all of the ones if you add edges, all of the ones if you remove edges from T, G of T, and all of the ones that if you reverse edges from G of T. So then you add edges on these ones, you remove on these ones, and you reverse on these ones. Okay, then you compute the scores of all of those nodes, all of those graphs. So score of the first one, second one, third one, all of them, all possible ways of moving from G of T. Then finally you make your move. So after you pick all of the scores, you look through all of your scores, you find the maximum one, and then you move to the G of T that maximizes the score. Okay, so this will be T plus 1. So you move to the GT plus 1 that maximizes the score. And then you repeat 2 to 5 until you can't improve the score anymore, until any change will decrease the likelihood. So the intuition behind this greedy hill climbing approach is that we make a change that best improves the score until no more improvement can be made. So here's an example. Let's start off with this network here. So cloudy, sprinkler, rain, and wet. So we calculate the probability of the model given the data using our Bayesian or scores or whatever. And from there, then you have to you then move to you now have to visualize all possible changes to this. So all possible additions. So there could have been one would be cloud to grass wet. All possible deletions, maybe you delete that node. All possible reversals, you look at that, right? So there's obviously a lot of them, but I'm only going to be looking at these two. obviously you have to list all of them, right? You can't only list 2, you have to list everything. So suppose that these are 2 of all of the others, and this one here where I reversed an edge, I reversed this edge over here, it gave me a score of 30, and then on this side I removed this edge and it gave me a score of 5. Okay, so obviously I'm going to look between 5 and 30, and I'm going to pick 30 because 30 is bigger. So I'm now on this side, so I eliminate now this, and I've now moved my GT plus 1 becomes this one. And then now similarly, I'm going to do the same thing again. I'm going to now look at, this is my new GT, and I can reverse this guy, flip it around, or I can add a new edge on this side here, like this here. And then look at, we have to now score those, and from here I can either move to a 90 or 120, and I picked the 120. Okay, so I picked the highest value. So now this is my new structure, and so I continue in this way until I reach the highest, until any change will decrease the score. So what is the computational complexity of this procedure? So it takes O(n) squared to score the initial network, okay? Because you're going to go to every single node, and you're going to have to score them. So the initial network needs to be scored. Okay, what k steps to converge, okay? And suppose that you've got a decomposable score. Obviously, the complexity will change if it's not decomposable. It takes k steps multiplied by n squared operator applications, right? For the operator applications can be to add things in, to remove things, or to reverse things, okay? And the number of families, I mean, even if it's 2n, it's still 2, it's still, even if it's 2n squared, it's still n squared, okay? Because in computational complexity, we just, what is the word? We just approximate. We discard lower order terms and constants. Remember from your data structures course with Richard? That's what you do. Okay, so then you end up with. So where does this come from? Well, it also incorporates the number of families, which is O(n). Okay, it incorporates the acyclicity check, and you do that using something called a topological sort. This just checks if the graph is acyclic, and the complexity of that is just the order of the number of edges. It's actually quite a simple algorithm. And then we end up with collecting sufficient statistics. And to collect sufficient statistics, we need to basically just run through our data once, okay, and we can collect all the sufficient statistics that we require. So you can run through it once and do k checks at every instance, but the point is that it'll be approximated to m. So the total complexity is this, and that is the initial, right, multiplied by k steps to convergence. K steps to convergence in the hill climbing procedure. These are the operations that are required. These are collecting sufficient statistics per family, and M is the family, and this is my acyclicity check that I had before. Okay, so this is my computational complexity of the structure learning with hill climbing with a decomposable score. Okay, if it's not decomposable score, it's not going to work. Then it'll be a different kind of complexity. Yeah, okay. All right. So the computational savings can actually be increased. So alongside having a decomposable score, which means that we don't have to decompute the entire graph structure anymore, we just have to compute the parts of the graph that changes. But on top of that, you can actually save more by keeping a heap of all of the different operators that you have, the score of the operators that made the change. So for example, you're keeping score of the operators in a heap, the score of the operators in a heap, and by doing that, you will have, because at the top of the heap, remember, you can model a priority queue, and the scores, what the highest scores will be at the top of the heap. So which means that you can update this heap in n log n time, all right, at every iteration of the n log n time, with every iteration of the algorithm, of the search procedure, and for every k time of the search procedure, and to get the optimal score, the optimal scoring operation, you can actually just have it at the top of the heap, which is O(1), to just extract it. Okay. Removing it, of course, is going to be log n, but I mean that's also not a big deal, right? Because you're only going to remove it once. You're going to add n times, but you're only going to remove log n, which is not a big deal. So isn't that wonderful? I mean, the complexity, look, this is not a crazy complexity. This is not a crazy complexity. This is something that's manageable. I mean, sure, it looks a bit scary because of all of the text that I've written around it and all of my annotations in red, but it's not a scary formula. I mean, you've seen worse things in this, I'm sure. I mean, you did AAA, and there was some, these different algorithms that were n3 and n to the power of 3 and so on. I mean, those are much worse. I mean, k doesn't even make a difference because it's just going to be n squared plus n squared plus n squared plus n squared. I mean, that's not even, where n is the number of variables, right? So I'm sure it's an adjacency matrix, but even with 1,000 variables, n squared is not that bad. So what do you get at the end of this? So at the end of this procedure, so let's say you started off the search procedure, you have an initial score here, okay? Then, so you started off, you're lucky, you ended up, okay, maybe you're not lucky. Let's assume that you're not lucky. So you have, this is my search space, okay? So this is these are all of the different scores I can get from my space. And I started off here, okay? Now this is my initial, okay, yeah, my initial network. I started off here. Okay, so what happens is that every time you move with your operation to a new structure with the operations from before, every time you move, you're moving k times to convergence, and you have to you're using the operations here to reverse or to add or whatever, right? You're actually optimizing based on the score. So you're increasing the likelihood of the data. So you're going up, and you're going up again, and you're going up again. So you find the next best network going up again, next best network going up again, and you can end up here at the top. Okay, that's great. So you can reach a local maximum. Okay, so look, there was other places that would have given you a higher score, but you happen to have just been put over here. So how did you get from here to here? Okay, that's the big question, and there are some techniques, but let me first explain these two things. So the number one, it's the local maximum. Number two, what could have also happened is you could have ended up on Table Mountain like this. Okay, you could have started off here, and then you went up, 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 up. But now any change you make doesn't increase the score because it's flat here on the top. So any change you make is giving you the same score. That is called a plateau. So the other neighboring networks give you the same score. So there's some approaches that you can use to actually get rid of this problem. So the first one is that the first one is using a taboo search. So this here avoids doing the same moves again by keeping a list of the moves that you've done for the last 50 moves that you've made. Okay, so so you make a few moves and you write them down, and then you try not to do those moves again. And this technique actually helps. It helps you to avoid a local optima. Random restarts is also a really cool way. There's two ways of doing random restarts. So the one way is to suppose that I'm here. So you start randomly at this position, and then you optimize it. Then you start randomly at this position, then you optimize it. Then you start randomly at this position, and you optimize it. And this position, you're keeping track of where you were and which one gave you the highest score. And then hopefully you would have done this enough to find a reasonable optimum that's higher than any of the other ones that you've tried. And that also seems to help. I mean, intuitively it makes sense, right? Obviously, the only problem is that the search space is so enormously large that even randomly restarting is a problem. The other way you can use random restarts is by suppose that you have a hill climb, like something like this, and you start off here, okay? Then you end up by optimizing the scoring function, you end up here, and you're looking here, and then you feel like you can do better. So what you do is you take a series of random steps, okay? And you take a series of random steps, and then you start optimizing again, and with the hope that you would then walk out of this local optimum and find a global one or better one. So that's the other way of using random restarts. The final way is when I think about this way, I think about when in the olden days when the TV used to not work, and I don't know if your dad was like my dad, but he would hit the TV on the head and then the signal will suddenly work, right? So you'll be watching TV, and in those days there was those antennas, and then the TV stops, the thing gets a bit fuzzy, you knock it on the head, you just give it a good slap on the head on the TV, and then it starts working. So, and I'm sure you've done it before on your cell phone, or maybe the calculator started to malfunction, and you give it a good smack, and it just worked. And that's how I picture this method. So here we try to add a little bit of noise to the data, or we perturb the data slightly to change the landscape of the search procedure, of the search space. And then hopefully the search procedure will be able to find the local optima. So we try to give it a good shake, or clap, or whatever. We give the data a little bit of a shake or a clap, and hopefully then it'll try to it'll be in a better position to be optimized on. Okay, so it works. It works very well. Okay, great. So I spoke a lot about greedy hill climbing, right? Okay, I spoke a lot about greedy hill climbing, but there are other methods as well. I'm going to speak about one of these methods. And why only one? Because greedy hill climbing still does better. With random restarts and taboo lists, it performs better than most other methods. And this method is called simulated annealing. And what simulated annealing? It's from metallurgy, where when they make metal, they heat the metal, then they cool the metal, then they heat the metal, then they cool the metal, then they heat the metal, and they do this continuously, heating the metal and cooling the metal until the metal is really strong. The analogy here translates that we occasionally move to worse structures to explore a wider search space and escape local maxima. And then we start optimizing the score again. And then we continually move to worse structures and then optimizing. So it's kind of like this random restart kind of thing, but with the specific goal of going to the worst possible. So random restarts was randomly moving. Here we intentionally going down, and then we're going up, and we're going down, and we're going up. All right. So that's now well done. You've learned about structure learning. This is possibly one of the most difficult topics in machine learning, and the reason for that is because of this the whole Bayesian score and the way of thinking about. But to be honest, I think everything Bayesian is a bit more difficult because it costs a lot more to think properly. And the Bayesian way of thinking is clearly the superior way. It's clearly the better way of thinking. Maybe that's why it's more difficult. Maybe better thinking is a problem. Maybe that's why most of us don't do better thinking, right? If better thinking was so easy, maybe all of us would be smart. Okay. I'm going to talk about comparing parameter estimation from the last lecture and structure learning from this lecture. So parameter estimation, in this particular graph, we have the number of samples at the bottom. We got KL divergence here, which is the entropy. So this is the KL divergence between the true distribution and the learned distribution. Okay, so your true distribution and your learned distribution. This is the distance metric. Okay, it's a distance metric, and okay, there's too many p's there, right? So it's the true distribution, the distance between them. So the smaller the KL divergence, the closer they are, which means the more similar they are. The larger the KL divergence, the more dissimilar they are. That means that the learned network has nothing to do with the true network, and if it has approaches zero, then the true network is close to the true network is close to the ground truth network. I mean, the true network is close to the learned network, which is what you want. So in other words, you want small values of KL divergence. This is also called entropy. If anyone talks about entropy, this is what they're talking about. Well, in the context of different things, right? In trees, entropy means something else. I think in graphical models, if we're talking about entropy, we all talk about well, sorry, okay, that's a bit of a broad statement. This is relative entropy. This is relative entropy. Relative entropy and KL divergence is the same thing. Okay, so what this graph is going to show you is that Parameter learning is not much of a more structured learning is not much of a more difficult problem than parameter learning or parameter estimation. So the dotted line is parameter learning. So here we are given the true structure. This is the true structure, parameter learning, okay? And this one is the learned structure. So you learn the structure using the methods that we showed you, and you learn parameters plus. So you learn the structure with the parameters. So can you see here that the parameters, learning the parameters with the true structure works very nicely. I mean, as the number of samples increases, it goes lower and lower, so it gets very close to the true distribution, almost approaching zero. However, learning the structure from scratch and learning the parameters at the same time, which is the solid line, is not that far behind learning the parameters with the true network, right? I'm sure it deviates a little bit here, but it gets back on the right track. And look at the error bars. They're all generally in line. They're all going smaller and smaller and smaller. So this means that structure learning, empirically, right? Structure learning is not so much more difficult problem. It means that it's working. The stuff that I showed you in this lecture works. It works really well. And even look for a large number of samples, 50,000 samples, you can't even tell the difference anymore. I mean, so what if you had the true network? I can learn the true net. I can learn a network that can give me really good prediction. Okay. So this was a difficult lecture. Let me write it here. Lecture. Okay, this was a difficult lecture. You know, the reason I became a lecturer was so I can write on the board. And then COVID happened and I couldn't write on the board anymore. But now I'm so grateful I can write on this writing tablet, and it all comes very nicely on the screen. So at least now it wasn't, all those years of studying wasn't in vain. I can still write on the board. And okay, so in the summary here, okay, why do we need to do structure learning? We need to do structure learning for density estimation because density estimation is one of the goals, and also for knowledge discovery. There are many approaches to structure learning. There's constraint-based methods, score-based methods, and Bayesian methods. Okay, these are three approaches, three of the foundational approaches. And score-based methods, when we speak about scores, we speak about the likelihood score, the AIC score, the Bayesian score. We also speak about priors like the K2 prior, the BDE prior, and so on. We sometimes also talk about priors in the context of graph priors, not just parameter priors. In terms of likelihoods, we have two different kinds. When we look at this as a maximum likelihood estimation problem with the likelihood, we looked at the maximum likelihood. And when we looked at this in the Bayesian context, we considered the marginal likelihood, okay, which is much better. It's much better, much more realistic. And this marginal likelihood generalizes better to new instances. We also saw that maximum likelihood estimation provides an over-optimistic view on the parameter value. So in terms of priors, as I've said before, you've got your parameter priors, but you also got structure priors. You can use a tree as a prior even. You can use a random graph as a prior. You can get an expert to give you a prior. And the expert might not know all the variables, but they might know some of the variables, and knowing some of the variables reduces the problem exponentially. Okay, so having an expert just put together a very small model, even if it's a stupid model, it's perfectly fine. It's a starting point, and you can leverage on that. It reduces the search space exponentially, and that provides a good way forward. And then finally, there's lots of ways to perform the structure search. So you can learn trees using the maximum weighted spanning trees, and you can learn graphs using things like simulated annealing, or you can use greedy hill climbing, and lots of different graph procedures that also assist in learning the structure. So that's all for this lecture, and I hope you learned something. I know it was a bit dense, but that's why it's a video. You can always go back and go over things again. All right, all the best. Take care.